Hi all, I'm Shashi. I'm a PhD candidate from University of California, Irvine. In today's talk, we'll be talking about privacy from birth. This is a joint effort from Ivan Soyon, who's also a primary co-author, and Jean. Okay, so today's topic is IoT. So these devices make our lives comfortable, easier, and safer, and they easily, seamlessly connect us to the outside world via internet. And however, any vulnerability within these devices could lead to chaos, and especially the things which are pertaining to human privacy of humans. And if you see since the last decade, there are multiple attacks on door locks, smart fridges, and cameras. So we might want to be a little scared about these things. So these devices are ubiquitous. They are present everywhere, and they are diverse in nature, and they are also growing in number. We typically see them in houses, offices, public transport, industry, automation, and automobiles. They perform two or three of three tasks, which are like sensing, actuation, or controlling both of them. Sensing is sensing the ambient temperature or ambient environment, and actuation is causing a change in the environment. Typically, these devices are deployed at the low on the edge, and they are and low end spectrum. And you have higher end IoT devices or smartphones controlling them. They often perform critical tasks like sensing smoke in a house, or they also collect personal information like your smartwatch collects your heart rate information, and these, because of this importance, they are attractive targets for exploitation. So in today's talk, we'll focus more on the low end spectrum of these IoT devices, which are the microcontroller units, MCUs. So these have low cost, low power, and they are of small size. They need to fit everywhere, and they need to consume less battery power. They have a very low computing power. That is, they have single core CPUs with 8 or 16-bit architectures, and they have 8 to 16 or 48 megahertz of frequency, and their memory is less than 128 kilobytes. And the most important trait of these devices that important for this talk is they have no security features at all. They have no kernel, they have no MPU, they have no MMU, not even a hypervisor or a TE. And they execute instructions directly from flash that they don't have any virtualization to load and compute. And so examples of such devices are TI-MSC430 and AVR Atmega 8. So this is a typical architecture of a low-end MCU. It has the core, which computes instructions from the programs in the flash, and then it has interrupt control logic and DMA, which work in parallel with the core, and they connect. These units are connected to the memory via memory bus, and this memory has ROM, a read-only memory, so it contains bootloader and things like that, which are embedded at manufacturing time. And then there is flash, where you have the programs, and we have the RAM, the data memory, and then peripheral regions, which contain which does GPIO task or any other peripherals. So there are two peripherals, internal and external. So the more interesting part is external, where these devices, MCUs, are connected to the external sensors like temperature sensor or LEDs. So when a sensing happens, what do you mean sensing here? Sensing is when let's say a temperature sensor gets activated due to some change in the room temperature, then this sensor will understand what's the ambient temperature, and it will convert that information into digital format, and it will be first kept at the GPIO memory. And after this, the programs in flash take it from the GPIO memory and start processing on it or computing on it. So this is how a typical sensing happens. And so how to protect privacy of sensed data on these tiny MCUs? This is the primary question we'll be answering throughout the talk. So these are low-end MCUs, and they often collect sensitive information like heart pacemaker, for example, and they have no advanced features like TEs, or they cannot run fancy crypto like public key cryptography because they don't have much computing power. So, okay, simple idea here would be, why not just encrypt the information and send it out? So let's say we have the smartphone, and there is a thermostat, an example, a low-end device, and authenticate both the endpoints. After authenticating both the endpoints, now collect the sensor data on the thermostat, encrypt it with the key known to the controller, and send the information back, encrypted information back to the smartphone, understand it. So, however, if you zoom into this device, it has this MCU that is marked in red over there, and then there is LED which takes the analog information. So, and this MCU can, which has a software which does the encryption, right? So, and this software can still be compromised because there is no protection for these low-end MCUs. And yeah, so there are techniques which ensure software integrity on these low-end devices. They are like remote attestation, proof execution, and several other services. However, these services primarily aim to detect if the software on the device is compromised, but they cannot really prevent this compromised software to leak information. So by the time the controller knows that something wrong on the device, they can be pretty much sure that the data is already leaked. So how to guarantee sensor data privacy even if the software on these tiny MCUs are compromised? So the prior work we have just seen, they are based on detection algorithms, or they assume the software is benign, and there is no TE or OS to rely upon. So now we propose privacy from birth. So how do we define privacy from birth? So all the traces of information of sensor data from its birth until it leaves the device, they should be protected. So what do we mean by birth here? The birth is whenever the data becomes digital, that the ambient sensing or the ambient environment, when you understand the stimulus of the environment stimulus and then you convert analog information to digital, that is where it takes birth. And after that, it could be tainted at multiple places within the memory of the MCU. For example, there are two major places that it could be tainted. First one is the GPIO peripheral memory region, where it first originates. And there is also another way of data getting originate here, not only via GPIO memory, but there's also ADC, analog to digital converter. If the analog sensor does not implement converting analog to digital information, then the sensors might want to use ADC here, which are internal peripherals, and these ADCs place their information in the other peripheral memory region. So from here on, when I say it's GPIO memory, it's basically the memory, the peripheral memory, which could potentially contain the information. And the next part, the traces of this information could be found in the RAM, where the software reads and processes on it. So yeah. So what are the goals of PFB? The first goal is to prevent access to GPIO memory region and only allow authorized software to access it. The second one is ensure safe execution of the software. Make sure that the traces are also protected. So how does this achieve data privacy? That is, only the owner of the device who authorized the software can control what software can actually read the information. And the next one is, if this software can implement an encryption algorithm, and also if it makes sure to erase all the stack that it used after its computation at the end, then all the traces are erased and also they're encrypted. So nothing can be leaked. And now let's go into VERSA. This is Verified Remote Sensing Authorization architecture. VERSA provably implements PFB goals. And it's a hybrid architecture which has both software and hardware code components. So if let's say this is this short or less condensed architecture of this MCU, then VERSA has two components. One is the hardware component, which sits in between the core, or which sits along with the core, which accessing and checking what CPU is doing. And also there is another part of VERSA which sits in the memory, in the ROM region, which also both the software and hardware components act in tandem to provide protection of sensor data. And VERSA's workflow. So we have this controller and we have the device where we have the where VERSA is enabled. So GPIO memory is always locked by VERSA hardware. That is, it does not allow any software on the device to access it. So when the controller wants to read something from this MCU, then it will authorize using authorized procedure. That is, it will authorize a software, and it will generate something called as an authentication token, which corresponds to the proper software. This is typically implemented using a HMAC, or any attestation algorithm can do this. And this software and the authentication token are sent to the device, and software is installed on the device. So there is also another way of doing it. Instead of always sending the software, you can pre-install the software and make sure whenever you want to use it, or send a new A token. Make sure it is fresh by using a nonce. And once it is there, Versa software component implements something called as Verify. This Verify takes this software and the A token, see whether these two are corresponding to each other. If they are not corresponding to each other, then GPIO memory is still logged. But if they are corresponding to each other, then it unlocks the GPIO memory for you to access it, or for the software to access it. And the next one is we invoke atomic execution of this software. That is, we need to make sure that the software is not disturbed by any other program on the MCU, not even DMAs, not even interrupts or any other software. And after computation, the software can choose to encrypt the results and send back to the controller. So I say choose here because there could be some applications where the controller need not want to have any results, but they could just have a local actuation happening. For example, in a thermostat, if you set it to some temperature, if the temperature is below that threshold, then the air conditioning can start heat up. It need not let the controller know all the time. So yeah, this is the basic workflow of Versa. And now let's go into what are the features of Versa. The first one is access control to sense data. That is, only authorized software is allowed to access GPIO. And otherwise, any other software, if trying to access GPIO or any sensitive information, we will reset the device. So we won't allow it by resetting it. Anytime it does, it will just reset. So this is how we maintain this latch. And then atomic execution of authorized software. That is, no interrupts or DMA are allowed during Versa software using authorized software execution. So what could happen is if there are interrupts, then you can just interrupt the execution of the software, and then you can extract secrets from the tainted information in the stack. So that shouldn't happen. So that's why Versa locks it. It doesn't allow any interrupts or DMA. And then S need to start from its legal entry point, that is the first instruction, to its legal exit point, that is the last instruction. And also S must implement self-cleanup routine that erases its stack after execution. So the reason that we want S to implement this cleanup routine and not Versa, because so S, the developer who writes S will know how much stack it uses. So it's easy for them to actually go ahead and clean it up. But on the other hand, if Versa needs to clean it up, then you need to clean up the whole DRAM, and that is huge, and that will incur a lot of performance cost. And the other feature of Versa is data erasure at boot. That is, if something happens during, any violation occurs during atomic execution or during access control, then the way Versa acts is by resetting the device. That means whenever you, during execution, if you reset, then there could be some information in the stack left over, and when you come back after reboot, malware on the device can still access this information and try to extract some information. So we don't want that to happen. We want to make sure that the stack is cleaned up at any point of time. So we need to clean up at boot. So make sure there is no information left. And now let's talk about some hardware properties that we implement for Versa. That is, let's say authorized software is placed in configurable memory region called executable region, ER. And let's say the PC reaches an instruction called IOT when the ER software in the ER is authorized to access GPIO. So this is how we'll get to know that a software is authorized. So Versa resets the device whenever certain violations occur. That are these. So we lock GPIO access by default to every software on the device, and unlock GPIO access selectively to only authorized software, and that too only while that software is executing. So these are properties. So due to interest of time, I won't be going into detail of these properties. But the second property here is read GPIO, and if the PC is not in ER, then we reset. So yeah, and atomic execution of the software. So when ER is executing, there should be no DMA or interrupts occurring. If it occurs, then you reset. And similarly, S need to start from first instruction and end at last instruction. And if ER is modified at any point of time, or even before, after authorization and before starting ER, then that means you are not authorized. We should not be authorizing a wrong ER. So whenever this modification occurs, we revoke access to GPIO, and we need re-verification of ER again. That is the last property. And so this is a sample state machine for the core ones. So we started the initial reset state, and we go to lock state. So whenever the authorization hits, we go to unlock state. And then if something happens at this unlock state, if some other software is trying to read GPIO, we reset. And as soon as you complete the software, you go back to the lock state. So this is a formal verification pipeline. So we implement Versa in Verilog. So there are several hardware modules. And these hardware modules adhere to these sub-properties that we have seen in the previous slide. And then there is a machine model, which are we axiomatize the MCU that we are using, and we plug in as these are assumptions and axioms about the machine. And then we use new SVM symbolic model verifier to check whether this Verilog code is maintaining all the properties of these properties. And after that, we use Spot to actually make sure that these properties that we wrote actually mean some access control GPIO or atomic execution of S. So it's a two-way proof. And then we implement Versa software using Hackle's formally verified library. So we get the verifier routine with that. So all these things together form PrivacyfromBirth. And implementation, Versa is built on OpenMSP and synthesized and deployed on a basis 3 FPGA. So we use Raised for implementing verifier routine, which is a formally verified remote attestation architecture. And then our implementation open sourced at this particular location. So the hardware overhead of Versa is like this. So it has 13% extra. It needs 13% more hardware on OpenMSP core, and it has 10% more hardware overhead on Raised, which one of the subroutines that we use. And comparison to other architectures, Versa is comparable to other architectures, which are hybrid architectures, both software and hardware co-designs. On the other hand, there is Sancus, which is very fast compared to all these hybrid architectures, but it's purely built on hardware. So conclusion is Versa hardware overhead is comparable to other hybrid architectures. So, and runtime for Verify. So we evaluated runtime on Verify on 3 cases. And we saw that so naturally, since the Verify is implemented using HMAC, which grows, the time taken for HMAC implementation grows as the binary size increases. And that is linear growth. And the main takeaways are like this. PrivacyfromBirth. This is an end-to-end privacy assurance architecture for low-end IoTs. We formalize and define PFB in our paper. And there is Versa, which provably implements PFB. And it also basically implements a minimal formally verified hardware. And we deploy it on OpenMSP, and it has 13% hardware overhead. So this is the paper link and GitHub link and my contact.
All right, let's thank the speaker. We have a couple of minutes for questions.
Hello, Shizhen Zhao from the Ohio State University. So very great work. I have a question about, actually it comes about the cost. So you said that your project is deployed on, your system is deployed on some like very low cost MCU. So I know in your implementation you use FPGA, that's not feasible in production, but how would you feel about the cost if you make your system into ASICs, like those mini chips?
Yeah, so that's a great question. So we implement it on OpenMSP. So this is an open source architecture of MSP, which is from Texas Instruments. And this OpenMSP is very close to the real MSP. And whatever additions we have from Versa hardware, they need few more D flip-flops and few more like some hardware components which scale like 13% over the OpenMSP. So whatever cost is required to make an OpenMSP chip, if you add 13 or 15% extra on it, then you could get this in the real world. But obviously, this is a research prototype. So if it actually gets into production, I really want to see if it gets into production. But yeah, it might take a while. Yeah.
Okay, thank you.
Yeah.
Hey, thanks for your talk. Alejandro Mera from Northeastern University. So I would like to know what are your thoughts about the applicability of your solution, considering that these or these type of security features are not available, and you are proposing something that is even academic.
Yeah.
Thank you.
Yeah. So yes. Yeah. So this research is targeted for low-end devices, which, as you said, we don't get any security mechanisms like MPU or MMU. So if you want, and these devices do a lot of critical computations. So if we want security on these devices, the only way to go forward with this is to either use let's say a trust zone enabled devices, which are slightly higher end, slightly costlier, and then you get all these things for free. But if you still want to be in the low end spectrum and still want to use, then there is no other way except to use this. So yeah, it's a trade-off. I mean, currently they are not available, so the only thing available is trust zone enabled devices for low end. So that needs a little more cost. But this one has much less cost when you put into assembly line and try to manufacture them.
All right, let's thank the speaker. Thanks, Joshi.